Now let's take a look at equilibrium constants. All right, so again, when something's at equilibrium, the rate of the forward equals the rate of the reverse. And so what the reaction is trying to do is it's trying to maintain this ratio of the products to the reactants. So the ratio is K, our equilibrium constant. So if I have a generic reaction with coefficient A, species A, plus coefficient B, species B, what I do is I have the concentrations of each of my species raised to the coefficient next to them. All right, so let's practice writing some of these. Okay, so here's one right here. So K is going to be equal to the products over the reactants. So I've got some hydrogen gas. Now I have a 2 as the coefficient in front of the hydrogen. So this is going to be raised to the power of 2. There's no coefficient on that sulfur there, so it just looks like that. And then I've got some hydrogen sulfide gas there. I have 2 of them. So we get raised to the power of 2. Okay? So try this one. All right, let's see if you got it. So we have coefficient 4, so it's raised to the 4th. Okay. Raised to the 2nd. All right. Okay, try this one. All right. And for good measure, try one more. All right, so those are our K expressions. Now, it's not enough to just write K expressions. Let's actually use one and see if we can't figure some numbers out. So we have this reaction here, dinitrogen tetroxide gives us 2 nitrogen dioxide. So let's calculate K if we have some equilibrium concentrations here. All right, so our K, we're first going to write the K expression. Okay, once we have our equilibrium expression written, now we can plug our numbers in. Okay, so our nitrogen dioxide was 0.92. We're going to raise that to the 2nd power. And then we had 4.0 on the bottom. All right, so when we do the math here, we get 0.2116. We have 2 sig figs, we get 0.21. Now, when we have equilibrium constants, the units actually vary from equilibrium to equilibrium constant. So my concentrations are in molarity. So when I plug just the concentration terms in, here I get molarity squared, because I have a molarity times a molarity over a molarity. All right, so I can expand that out. All right, and so this and this will cancel. So for this particular equilibrium constant, my units are in terms of a single molarity. This just, again, varies from equilibrium constant to equilibrium constant. I've seen units in inverse molarity. I've seen units in molarity cubed. It just matters what everything gets put together when you figure out how all the molarities cancel out. Okay. All right, so here is another problem, this phosogene. Okay, so we've got some equilibrium concentrations of our different components of this phosogene. Okay, so before you switch to the next slide where I'll write out the solution, I want you to try and put all this together. So this is just like the one we just did, and see if you can figure out the equilibrium constant for this particular reaction. Okay, so pause the video, try it yourself, and then unpause and check your answer. All right, let's see how you did. So You're going to get an expression that looks like this. Everything's 1 to 1 to 1, so we don't have any coefficients to raise anything by. So we're going to get all right, and this one's also going to be in terms of a single molarity, the way it cancels out. And so you should get 4.63 times 10 to the negative third molar. Okay? All right, so here's another one. We've got an equilibrium constant this time, and we have concentrations of 3 of our species at equilibrium. And what we want to do this time is we want to find the concentration of the water vapor. Okay? All right, so what we need to do is first write our K expression. Okay, so there is our K expression. So now we need to solve for the H2O. So we'll rearrange this, and what we end up getting is the concentration of the water is going to be equal to the carbon monoxide, the hydrogen cubed, over K times the methane. Okay, and then it's just a matter of plugging it all in. So now okay, and then we get okay, and we put that all together, we are going to get 0.526. All right, we have 2 sig figs, so we'll get 0.53 molar as our concentration of our water vapor. Okay, so that's how we can use our equilibrium constants. Now, we do like to specify sometimes what type of equilibrium we're talking about. So sometimes you'll just simply get K. That's just an equilibrium constant. Now I have various other Ks listed here. These are all still just equilibrium constants, except some of them are very specific. So Ksp stands for the solubility product constant. Now, when we write the Ksp expression, right here, notice that it's only got the products in it, okay? Pure solids, they don't really have a concentration that changes. So pure solids don't appear in an equilibrium concentration expression. Same thing over here. I've got my autoionization of water. Well, what doesn't appear in that equilibrium constant expression? The liquid water. The liquid water is there in such an excess amount, it doesn't have a concentration that's going to change at equilibrium. It's there in so much that anything that happens with it is negligible and won't affect anything. Okay? Our equilibrium constant expression for the ionization of a weak acid, right? Same sort of a thing. We've got 2 of our products. We've got 1 of our reactants. In this case, it's the hydrocyanic acid. But what doesn't show up? The liquid water. And we can do the same thing for a base. Okay, again, what doesn't show up? That liquid water. So pure solids and pure liquids don't show up in our equilibrium constant expressions. And again, all of these are just an equilibrium constant expression. We just give them some subscripts so we know what kind of equilibrium we're talking about. So the Ksp, solubility of a mostly insoluble salt, Kw, Kw is for water, Ka for an acid, Kb for a base. Okay, let's look at some of these Ksp values. So if you look at them, a lot of Ksp values, most of them are really, really small. This means that the reactants are going to be heavily favored, and so not much is going to dissolve. I think the worst one on this particular list is the copper 2 sulfide with a 10 to the negative 36th there. Not much is going to dissolve. But when we think about Le Chatelier's principle, if we want to dissolve something that is infinitesimally soluble, what I can do is, let's say I put something else into solution that will interact with one of the ions that's formed. Well, Le Chatelier's principle says I need to relieve that stress. So if I remove one of the product ions, now I'm going to dissolve another one of my reactant solids. If I remove a product ion, I'm going to dissolve another one of my reactant solids. So we can actually get these things to dissolve if we put something else in solution that's going to draw it out. Okay, let's practice some of these because this also will help practice some nomenclature too. So first we're going to write the dissociation equation and then we'll try a Ksp expression. So magnesium carbonate. Okay, so I have solid magnesium carbonate. It will dissolve into magnesium ions plus carbonate ions. Hey, again, in my Ksp expression, I'm not going to put my solid, so my Ksp here is going to be magnesium and carbonate. Okay? All right, let's try another one. Iron 2 hydroxide. Okay, so we're going to get all right, so there's your iron 2 hydroxide. We'll get some iron 2 ions plus 2 hydroxide ions. Okay, again, pure solids don't appear in that expression. So our Ksp, we'll get the iron 2 times that hydroxide. It's got a coefficient of 2 in front of it, so we will square that. Okay? All right, so here's 2 more. I want you to try these. Stretch your brain, remember that nomenclature, and write the formula, write what it dissociates into, and then see if you can get the Ksp. Okay, let's see how you did. So, calcium phosphate. All right, so we're going to get 3 calcium ions and 2 phosphates. All right, and then my Ksp, I'm going to raise that to the power of 3, raise that to the power of 2. Okay, and then our last one, our silver sulfide. Two of those. And one of those. Okay. All right, and so that is how we write our Ksp expressions. Right now, we can take a look at some stuff with acid or base dissociation. So in this case, we're just going to use that Kw because we just want a hydrogen ion and hydroxide ion concentration. Well, we need one to get the other. So we have some barium hydroxide here. We have 0.045 molar. So we can take our 0.045 molar barium hydroxide. And in this formula, I have 2 hydroxide ions for every 1 barium hydroxide. So I end up with 0.9 or 0.9 molar hydroxide. Now Kw is our H plus times our hydroxide. So if we need H plus, we rearrange. So we'll get our 1.0 times 10 to the negative 14th is our Kw over our hydroxide of 0.090. And we're going to get 1.11 times 10 to the negative 13th. We have 2 sig figs, so we'll round to 1.1 times 10 to the negative 13th molar H plus. Okay? When we look at our acids and bases, the strength of an acid depends on how much of that H plus is formed. So the smaller the Ka value, the less H plus is formed, okay? So the smaller the K value, the more it favors the reactants. The larger the K, the more it favors the products. So when we get down to super weak acids, they have really small Ka values, which means they don't form a whole lot of product. The product for acid dissociation is that H plus ion. So we don't dissociate a lot, we don't form much product. We don't form much product, we don't have much H plus ion, so we are not very acidic. All right, so the smaller the Ka value, the less acidic a weak acid is. The larger the Ka value, the more acidic a weak acid is. Okay. When I look at polyprotic acids, so something like phosphoric acid has 3 ionizable hydrogens on it. Okay, it's a triprotic acid. So what we actually see is that we don't get all 3 hydrogens coming off at once. They come off successively. So a polyprotic acid will have multiple Ka values. If it's triprotic like this one, it'll have 3 Ka values. If it's diprotic, it will have 2 Ka values. Okay, and so the first dissociation is always the easiest. Each successive one is higher, so the Ka value gets successively smaller as you go down and take off each proton. Okay, so lots of things we can do with equilibrium constants.